Hello everyone, this is Dr. Feng Wang again, and today we are going to continue the reactions of carbonyl compound. So all the nucleophilic either addition reactions to aldehyde and ketone, or the nucleophilic substitution reactions toward acid chloride or esters we have discussed so far. We need organometallic region, and all the organometallic region to do these reactions are either magnesium region, very reactive, or the lithium region, the carbon-lithium bond, the super reactive region, because the carbon either connect to magnesium or the carbon connect to the lithium region. Both carbons here bear a lot of negative charge, so they are very reactive. So we also know that there is a third organometallic region. It's called a cuprate or copper region. And the cuprate or copper region, they are less reactive than the lithium region or magnesium region. Magnesium region we also call Grignard region. So I consider, Grignard region or Grignard reaction one of the top 5 organic reactions. So these are very important reactions. We need to learn the reaction product. We also need to fully understand the real mechanism of the whole process, either nucleophilic addition reaction to aldehyde or ketone, or the nucleophilic substitution reaction to ester and acid chloride. So we are going to discuss the less reactive copper region today. Well, because they are less reactive region, they want to attack carbonyl carbon here. Only to the carbonyl carbon here, the carbonyl carbon bears a lot of positive charge. Or the leaving group here needs to be very good leaving group, because I'm weak to attack you. I need your help. Either you bears a lot of positive charge, or the substitute here, you are very good leaving group, but you are willing to leave this compound. So I can do the substitution reaction. That's why the less reactive cuprate region normally react with the acid chloride, because acid chloride is very reactive. The chloride or bromide, they are very good leaving group. Remember the term I generated, clean, Cl, clean, Cl acid chloride. That's the most reactive carbonyl compound actually. So it will react with the cuprate region. So this is the substitution, nucleophilic substitution reaction. Again, the carbon here, the carbon connected to this copper atom, there's a little negative charge. The negative charge is going to attack this carbonyl carbon. The chloride serves as the leaving group to form the final ketone product. At this moment, you see, this is also carbonyl. This is carbonyl. This carbon bears a positive charge. This carbon bears positive charge too. But the reaction will stop here. Even you have more cuprate region, this carbon still bears negative charge. It's not strong enough to attack this carbonyl carbon, because this R group, this ethyl group, now I'm not a good leaving group. I don't want to leave this carbonyl group. That's why stops. Reaction stops here at the ketone group. If we have a lithium reagent or magnesium reagent, because of the first carbon here, suppose this is magnesium or lithium, the negative charge here is very, very high. You don't want to leave, that's alright, but I still attack this carbonyl carbon to form an alcohol molecules. Or if you have a chloride here, alright, I will attack this carbonyl carbon. Again, cuprate reagent, they are less reactive, they react only the very reactive acid chloride. Another molecules that is very useful to do a lot of organic synthesis is epoxide molecules. Basically, we have a carbon-carbon oxygen 3 membrane epoxide. Again, this ring has a very strong strain. It's always love to pop off. So either a very strong reactive lithium reagent or very reactive magnesium reagent, or even the less reactive organometallic cuprate reagent is going to react with this epoxy molecule or epoxide, because the strength is so strong here that helps even for the less reactive cuprate reagent can open up the epoxide ring to form oxygen anion first, then protonation of oxygen anion, the alcohol molecules. This is more like a SN2 type of reaction. The carbon here, which bears positive charge, will attack from the backside of the leaving group. In this case, this bond will, let's see, this reaction, the R will attack this carbon actually. R bears negative charge, attack this carbon, and this bond breaks, and this part serves as a kind of a leaving group, just leaving this carbon but not the whole molecule. That's why we forms one molecule, not two molecules. This is SN2 type of a reaction we learned in chapter 7. A good example here, magnesium reagent react with the sample ethylene oxide. This is an epoxy molecule to form alcohol. So of the first steps of the nucleophilic attack, we need also the second step, protonation of oxygen anion. Well, this is a very simple epoxide molecule. Sometimes we have asymmetric epoxide molecule, like in this case. We have two hydrogen here, we have two hydrogen on the right side. In this case, we have to consider the reduced selectivity. So in this case, this carbon, which bears negative charge, either attack this side, the left side, or the right side, basically the same, because the left side and right side carbon, they are equal. But here in this reaction, the right side and the left side is not equal. Two methyl groups with the two hydrogen groups here. This is all the organometallic reagent. Again, they are, particularly for the first two, they are very strong nucleophile. They are also strong base. This second one, it is a mild nucleophile or mild base. So under base condition, remember under the base condition, the nucleophile here, this carbon, which bears the negative charge, will attack preferably this carbon because of the steric effect. It's very smaller that attack this side. That's why we have this type of alcohol form. So again, this is something we learned in chapter 9 or 10, the epoxide, the alcohol ether epoxide chapters. So we have two conditions, either base condition like this, or acid condition. And acid condition, some nucleophile can also open up this ring, but under acid condition, the nucleophile will preferably attack this carbon. So I just tell you the result, but if you don't fully understand this time, I would suggest you to review the chapter, I believe the alcohol chapter, acid condition, the ring opening reaction of epoxide molecules. These are also very important reactions. Well, the rest of this chapter, I think we are going to discuss the alpha beta unsaturated carbonyl compound. This is a very special group of carbonyl compound. They have some unique reactions with the organometallic reagent, and we are going to discuss the details. This is an alpha beta carbonyl compound. Well, first, it is a carbonyl compound. We have carbon, oxygen, functional group here. It's carbonyl compound. And also, it is special. We have the name. From the name, we can say it is special. It's called alpha beta unsaturated. Unsaturated means we have a carbon-carbon double bond. Why we call this alpha beta? It's because this is alpha position relatively speaking to the carbonyl group. This is carbonyl group. The first carbon attached to the carbonyl group is called alpha group. This is also alpha atom. This is also alpha carbon. And the next one is called beta. There is no beta here, but we have the beta on the right side. The second carbon is considered or called the beta carbon. Alpha beta unsaturated molecules. This is alpha beta. We have a pi bond between alpha and beta carbon. So this type of molecules is called alpha beta unsaturated carbonyl compound. Sometimes we label the four atoms here, actually basically oxygen, carbon, 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 alpha, beta, oxygen, carbon. And the order of number is oxygen is named the number 1 atom, number 2, number 3, number alpha, number 3. Beta is number 4. This is totally different from the IUPAC naming system. Why we have this 1, 2, 3 thing is because, this is a special system. There are many reactions around these 4 atoms. That's why we focus on these 4 atoms. We give them a number that's easy for organic chemists to communicate in the lab. And you will see this why we have this number things. Well, let's analyze the structure of this special carbonyl compound. Well, first, the oxygen, a very strong electron negative atom, is going to pull the electrons towards itself, or forms a resonance structure. So the pi bond, the 2 electrons move up towards oxygen, end up with oxygen, which has the 3 lone pairs of electrons plus a pure negative charge here. And this carbon end up with a positive charge because it loses 2 shared electrons towards oxygen. This is a resonance structure. Carbonyl group still bears the positive charge. This is similar to all the other carbonyl compound we learned in the previous lectures in this chapter. And why is this alpha beta is special? It's because of the alpha beta, the pi bond, the 2 electrons, can move towards this direction to form a new resonance structure, form a new carbon-carbon double bond here, and shift the positive charge from this carbon towards this carbon. This is a new resonance structure, and it is also a valid Lewis structure. Again, nobody wants to be charged positive, even positive or negatively. So by doing this, the positive charge actually shared between this carbon, the number 2 carbon, and the number 4 carbon, the beta carbon here. That's why, you see, that's why we have 1, 2, 3, 4. 2, we say this is 2, this is 4. So 2 positive charged carbon, either on number 2 or number 4. This is from the hybrid structure, we see oxygen, which bears a negative charge because it's strong electronegative. And also because of the resonance structure, oxygen bears positive negative charge. So number 2 and the number 4 carbon, or beta carbon, bears a positive charge. So if we have a nucleophile basically molecules bears a negative charge, nucleophile, negative charge, or a lone pair of electrons they want to share with others, they are going to attack number 2 carbon and the number 4 carbon. That makes sense? Because they bear a positive charge. They are not going to attack this carbon. They are not going to attack this carbon. They are not going to attack this carbon. If you have a double bond and like a beta gamma double bond here, you are not going to, this is the positive charge here. If you have a beta gamma double bond, it's not going to resonance its double bond towards this direction because you cannot jump this carbon. Only at alpha carbon positions. This pi bond can shift its position from here to here, from 2,3,4 to 2,3. That shift the positive charge from number 2 to number 4. That's why alpha beta is a unique carbonyl compound. It's beta gamma or gamma something else is not unique at all. You can just treat them individually. But for alpha beta unsaturated carbonyl compound, you have to treat them as a whole system, not only this carbon but also this carbon, because this carbon also bears positive charge. Let's take a look at the reactions of this alpha beta unsaturated carbonyl compound. The first one is the nucleophilic addition reaction. Basically, this is called a 1,2 addition. In this case, you don't have to consider the 3,4 position. You have a nucleophile. The nucleophile is going to attack this carbonyl carbon, form oxygen anion, followed by the protonation of the oxygen anion to form alcohol. So again, in this reaction, you don't have to consider the alpha beta position. It's only nucleophilic addition to the carbonyl group. In this case, we call it a 1,2 addition. This is actually very similar to other ketone molecules because nothing happens here. The second reaction is called 1,4 addition. So this is 1,4 addition. It looks like it's only react at the 3,4 position. You see, the nucleophile is going to attack the beta position. You see, because beta position bears a positive 2, the number 4 carbon, as well as number 2. So in this case, the nucleophile attack at this number 4 position, and the protonation of this carbon end up with the hydrogen here added at the number 3 position. From the the pure structures point of view, this is more like a 3,4 addition, like a 3,4 addition. So the carbonyl seems not involved in these steps. So, but why we call this is 1,4 addition? 1 means looks like 1. This is oxygen is when 1 reacted, and this is the whole process. Now let's take a look at the real process for 1,2 reaction and 1,4 reaction. This is 1,2 reaction. Again, for 1,2 reaction, it's only 1,2 atoms, carbon oxygen and carbon reacted in the whole process. Nucleophile is going to react with the carbonyl carbon to form the oxygen anion, and the protonation of oxygen anion to form some 1,2 product. You see, 1,2. Nucleophile added to 2 bears positive charge. Oxygen protonated. A hydrogen added to number one atom. This is 1,2 product. And let's take a look at 1,4 addition. Why we call it 1,4 addition, not a 1 or not 4, 3,4 addition reaction. The same molecules. Well, number 2 carbon here we know bears positive charge. Number 4 carbon also bears positive charge. So in this case, the nucleophile has the opportunity to attack the number 4 carbon as well. So whenever the nucleophile attacks the number 4 carbon, the 2 electrons moves towards to number 3 carbon. So number 3 carbon at this moment bears a positive charge. And whenever this negatively charged carbon is formed, it can do 2 things. First, okay, I want to protonate this negatively charged, basically like an acid-base reaction. This is base, this is an acid reaction, to form like a 3,4 addition reaction. So nucleophile added to number 2, protonation occurred at the number 3 position. It looks like, okay, it's a 3,4 position. However, let's take a closer look of this 1,4 addition reaction. This is a negatively charged carbon anion. So we have again, the whole thing is a system 1, 2, 3, 4. So we can draw a second resonance structure. This is second resonance structure. So this carbon is not happy. I want my neighbors to help me. This is how the neighbors help this negatively charged carbon. The 2 electrons forms a pi bond between number 3 and the number 2 carbon. Here, number 2 carbon forms the new bond, sigma bond, and the pi bond. So this pi bond moves up towards oxygen. So 2 pairs of lone pair electrons versus 3 pairs of electrons. So this 2 moves forms an oxygen anion here. So again, by doing this, I also call this is a good neighboring effect. The negative charge shift from number 3 carbon to number 4 oxygen. So if we compare these 2 resonance structure, I will say this one probably a better structure than this one. Why I would say this is because, you see, in this case, the negative charge is located on the carbon. But in this structure, the negative charge is located on oxygen. We know oxygen is a stronger electronegative atom than carbon. So, well, we are a team, we are brothers, but I'm stronger, oxygen is stronger in dealing with the negative charge than you, the carbon. So I would take more responsibility here to deal the negative charge. Okay, I want to share more negative charge here. So very likely whenever this molecule form, the intermediate form, this would be you know, the big brother. I would say this is the bigger brother, share more negative charge here. If this is the case, we are going to protonate this oxygen anion to form this molecules, the kind of alcohol protonation. And let's take a look at this structure. Basically, nucleophile added to number 4 carbon here. Hydrogen basically added to number 1 atom, oxygen. And we know this is a big brother, very likely this is the way to do the reaction. So that's why we call this is 1,4 addition reaction, because number 1, number 4 atoms were added hydrogen and a nucleophile. Alright, we also have another name for this structure. This is the anol. It's N, this carbon, this is the second atom carbon here. It is part of alkene. It also part of alcohol. So it is anol. Anol is not as stable as ketone. So anol will transform or tautomerize to ketone form. So to end up with this molecule, it's kind of, just look at the structure, it's a 3,4 addition product. But very likely this is the whole process to do the reaction, or this is the major role to do the reaction. And this product is the real addition product, is a 1,4 product. That's why we call the final product is a 1,4 addition product. Alright, it's time to take another break.